Yes, yes, yes.
All right. Are you guys able to see my presenter notes, or is it just my presentation?
Just the presentation.
It's not in
Just the presentation.
I'm sorry, I didn't understand that.
Just the presentation.
Okay, that's wonderful. Okay, so I would like to invite my co-researcher and co-coordinator Tanvi to, and we can begin the presentation.
Hello, everyone. My name is Tanvi Goyal. I will be presenting with Vaibhav today, and we will be sharing our research for solving the Schrödinger equation for the ground state energy of various atoms, self-consistent field methods in Python. So to start off with, quantum mechanics is one of the main models of the universe, the other being general relativity, describing the behavior and motion of microscopic or quantum systems. While it has led to numerous questions and reevaluation of models due to a lack of conclusion of particle interaction, it is still considered one of the greatest models of modern physics and has undergone much development over the last 2 centuries. The main reason that quantum mechanics was created in replacement of classical mechanics was due to the discovery that at the quantum level, electrons and other particles behaved as both particles and waves. So this couldn't be modeled by classical mechanics that accurately. So at the quantum level, due to this wave-particle duality, all calculations are most probabilistic, including that one of the position and momentum of an electron within an atom.
Okay, someone here who's not presenting has their mic open. If you're not doing a presentation, can you please close your mic?
All right, I'll continue then. First, the Schrödinger equation. Now, one of the most fundamental equations of quantum mechanics is the Schrödinger equation, as seen to the right. This is a differential equation that allows for the calculation of an electron's wave function that describes its quantum state, as well as the energy of the electron within the atom. H hat represents the Hamiltonian operator of the atom, which is the total energy of the atom. Psi represents the wave function of the electron, and E represents the energy of the electron. So while the equation is very useful, it is found that the equation falls apart when applied to multi-electron elements above hydrogen, where Coulombic repulsions between electrons causes the wave function calculation to be very imprecise. And now moving on to the self-consistent methods. So self-consistent field methods are computational methods approximating the Schrödinger equation. There are 3 main types: Hartree-Fock, density, functional theory, and post-Hartree-Fock methods. They all use recursive methods as shown on the image to the right. And it keeps reiterating the values in order to get an accurate or convergent result. So now onto the basis set. So the different ways of modeling initial wave function, Gaussian polar coordinates of SCF methods are the basis sets. So the left image represents the Slater-type orbital, otherwise known as STO. It is a more accurate but slower method. The middle represents the Gaussian-type orbital, or otherwise known as GTO. It's less accurate, but it's much faster. And to the very right is the summation of Gaussian types. And it is an increased accuracy with a change in number of functions used. So the size of a GTO basis set is how many functions are in the GTO in total. So the bigger basis sets are more accurate and closer to STOs. So since there are more functions in the GTO, it also affects the runtime. And now moving on to the Hartree-Fock method. So the equation on the left is similar to the Schrödinger equation. So F is the Fock matrix, or the sum of the Hamiltonian matrix and Coulombic repulsion matrix. C is the sum of the wave functions that we create using the self-consistent field method. S is the overlap matrix, which describes how the orbitals exactly overlap each other. And epsilon is the energy for each of the orbitals. And then we can add up all of the epsilon values to receive the total energy. And now moving on to the post-Hartree-Fock methods. So post-Hartree-Fock has multiple methods to it, but they all follow on the count for correlation energy in approximations. So correlation energy is the energy of electrons moving in other electron fields, but it's not counted for by the Hartree-Fock method. So that's why we have post-Hartree-Fock method. So different theories are used for different methods. So the CI theory, otherwise known as configuration interaction theory, it counts for correlation energy by changing the wave function guesses to account for correlation. The CC theory, otherwise known as coupled cluster theory, multiplies the Hartree-Fock wave function with cluster matrix T to account for correlation, and MP2, known as molar Plesset permutation theory, it changes the Hamiltonian to account for energy of correlation. So now moving on to our project goals. So our first project goal was to compute atomic energies for atoms from helium to argon. So we wanted to find the different commonly used basis sets, and we wanted to find different SCF methods. Our second goal was to compute atomic energies for atoms from argon to lanthanum. Our third goal was to find differences between basis sets in efficiency. So we wanted to find the difference between GTOs, and we wanted to compare the accuracy of GTO and STO. Then our fourth goal was to find the differences between methods in efficiency. And our fifth goal was to model trends between atomic energy and atomic number or mass number. And now handing it over to Vaibhav to present our findings.
Thank you so much. So before I continue, a lot of these topics do tend to just go over the listener when we're first presenting them. So I'm sure there will be a lot of questions. Please don't hesitate to ask questions after the presentation, because a lot of these topics are a bit exhaustive, to say the least. But regarding the basis or how we actually went about with our experiment, so if you guys remember, we were looking at Slater-type orbitals in our previous semester calculations, and all of that was done using Python. So we wanted to keep in line with the previous semester's experiments, and we tried investigating libraries that we could continue doing on Python, specifically for self-consistent fields. And we actually found an excellent library called PySCF, which stands for Python Self-Consistent Field, which is a peer-reviewed self-consistent field library based off of Python and C++ functions. It supports more than 10 self-consistent field methods, Hartree-Fock, density functional theory, and a lot of post-Hartree-Fock methods. Now, the downside is it only supports Gaussian-type orbital basis sets, so we can't actually translate our previous data into PySCF, but it kind of compensates for that by actually including a whole lot of GTOs. So it has numerous, almost 20 or 30 GTOs included within the package. And any other GTOs, if we want to actually experiment with them, we can get them from a website called Basis Stack Exchange and put them in what we call the NWChem file format. So we ran all of these programs on the ASDRP cluster because PySCF is only supported by Mac OS and Linux systems. And we kind of created functions to kind of make it much more efficient in doing the program. Towards the right, you can see that image. That was our function for Hartree-Fock. And we could just input in the 3 values into the function for atomic number spin, which is the number of unpaired electrons in this case. And then N was just in order to append it to a list that we could print as a table. And these tables were organized using a library known as matplotlib, which used LaTeX display in order to create graphs and tables in an aesthetic manner. So our first goal was calculating the PySCF. We're using PySCF in order to calculate energies from helium to argon, comparing it with our data from last year, our Slater-type orbital data. So we used 4 main methods. Restricted Hartree-Fock, which is just another name for a type of Hartree-Fock, molar placid perturbation theory, or for the people who are interested, it's second order, configuration interaction, and coupled cluster methods. And for our basis sets, we had a whole variety of basis sets that were included. The ones that we included were a mix of big, small, and medium-sized as defined by the Chemistry National Institute of Standards and Technologies. So STO3G and STO6G tend to be smaller ones. The CCPVDs tend to be medium to large. The 321s tend to be smaller. 631s are slightly bigger, and 631s are quite big. And then the CCPCVNZs, the last 3 are really big basis sets. And oh, I'm so sorry. Give me a second. There we go. Sorry about that, but none of these calculations from helium to argon, these were actually already calculated, and they are there on the chemistry NIST database. But we just wanted to try it from helium to argon so that we can get some sort of a test for PySCF and actually create a foundation for the other goals that we plan our testing or are in progress of actually testing. So observations. We had 2 major observations in do you need bigger basis sets for larger atoms? Actually, yes, this is correct. We do need bigger basis sets for larger atoms. We will be getting to that shortly as well, but exactly, since you have more orbitals, you want to get it to be more accurate. So your basis sets are generally going to be bigger for larger atoms. But just regarding helium to argon, we have these few 10 to 15 standardized, really commonly used basis sets, and that's what we actually experimented with PySCF. So goal 3, which was comparing basis sets and their accuracy, we were able to determine the accuracy of the basis sets by comparing the experimental ground state energy calculation from the physics NIST database to our calculations. We selected argon specifically to actually analyze these differences because it has the most electrons, which means it'll need the most wave function orbitals, and it'll also have the highest correlation energy and highest Coulombic repulsion. So it's the best in order to actually see how efficient these self-consistent field methods are. And so we first tested the accuracy of these methods. We can find the accuracy of these methods by comparing the values of the calculated energy to the experimental energy. And we got that for most of the values, CCPCVQZ, which stands for correlation consistent, it's a Dunning basis set quadruple zeta, which means it uses 4 major orbital functions. It sums up 4 major ones. But this was, and theoretically as well, CCPCVQZ is directed towards post-Hartree-Fock calculations, and it's the biggest on our list as well. So it made sense for that to be the most accurate when compared to the experimental data. Interestingly, for restricted Hartree-Fock, we actually got another big basis set nonetheless, but it was interesting to see that the basis that we got for that to be the most accurate was different. So we have to investigate why maybe we may have gotten different results for which may be the most efficient basis set in terms of accuracy. For precision as well, the most precise was the CCPCVQZ basis set. How we actually define the precision is how in detail we can get models of the orbitals and how in detail we can get the energy of the atoms. Now, if there's a greater correlation energy, that means the basis set is doing much more in-depth calculations for Hartree-Fock and then post-Hartree-Fock. So the one with the most correlation energy is generally the one with the most in-depth, most precise calculations, which was, of course, in this case, CCPCVQZ. The last thing that we did was we tried comparing the methods themselves and seeing which one was more accurate and more precise. So again, we kept argon as a control, and then we kept which we determined to be the best basis set, the CCPCVQZ as the control. And we tried comparing the different methods and seeing which one was closest to the experimental energy. And in order of decreasing accuracy, the highest was coupled cluster, second highest was configuration interaction, then molar placid perturbation theory, and then the last one was Hartree-Fock, which aligns exactly with what we expect from theory. One last note on this would be regarding runtime. So we are still trying to initialize runtime libraries. We do have some, but because of some issues in actually implementing it in the cluster, we have not been able to get like absolute quantifiable runtime data as of yet. But that is what we are actually testing now, trying to find libraries that we can get the runtime from. Relatively speaking, the runtimes also align with the theory. Your bigger basis sets tended to have slightly higher runtimes, and the more accurate the method was, it generally took much longer. So relatively speaking, restricted Hartree-Fock for all of the elements from helium to argon took maybe around 5 minutes, but with coupled cluster that took around maybe 15 minutes, also taking into account the lag when we were actually looking at doing the calculations on the cluster. And using these, we can actually, have observations for what we're going to do in the future. The most interesting of them, in my opinion, of course, will be extrapolating the data from helium to argon, from helium and argon, and actually going forward to explore uncharted territory and new frontiers, specifically from argon to lanthanum. So we did find through our literature review and just general research that data is there until krypton, and then from krypton onwards, there is no documented, comprehensive, or exhaustive database with any of that data. So the major reason as to why there is no standardized data after that, not even in the chemistry NIST database, is largely because a lot of those standardized basis sets that we were using and talking about from helium to argon, those tend to disappear, and we haven't calculated functions from potassium onwards. And it's exactly what Dr. McMahon had mentioned. For these, your standardized basis sets are just simply too small, so it's too inaccurate, and it's much harder calculating the smaller basis sets because you need a smaller number to describe a larger number of electron wave functions. So it's much harder actually getting those basis sets. You need to use more specialized and customized basis sets per group. So as you can see on the presentation, for like alkali earth and alkaline, you need some basis sets, and then for transition metals, you need some basis sets, and then towards the end, for the non-metals, you need other basis sets. Each one of these quite big basis sets that may take longer to run. And so because of this, and also taking into account the time constraints that we have within this semester, we wanted to stop at lanthanum, which is the beginning of the F block elements, which is the new F orbital. And not only is it because of the time constraints, it's also because F block brings in a whole new set of complexities regarding how many wave functions you need and what basis sets you need. So actually implementing that may take longer than just doing the other three blocks, so SP and D blocks. So we are going to be looking at post-lanthanum maybe towards the next semester, perhaps. Now, regarding goal 3, so we, in our previous colloquium presentation in the fall semester, we did identify that with our Slater-type orbital programs, we saw this general linear progression by around 2% in the percent error between the Slater-type and the actual energy. And we thought, maybe this may have been caused by correlation energy, or this may have been caused by the basis set errors themselves. So we decided to compare with the data we collected in this semester, and the data simply doesn't pan out. Your correlation energies are in the magnitude of maybe negative 0.6.6502 was the maximum. 0.6502 Hartrees was the maximum correlation energies. Comparing that with the error we got for a Slater-type, that was negative 96.6 Hartree. So clearly the error wasn't correlation energy, nor was it a problem in the basis set. It was most likely caused by a bug or an error, methodical error within the calculations in the program. So we went and revisited the program, and we found exactly that. One of the suspected error at this point was regarding the basis set. So what happened was regarding the density matrix, which, as I said before, the density matrix is what plots the electron density. So the probability of where an electron may be within an orbital. And this, of course, changes whether or not an orbital has one electron, which we call unpaired, or two electrons, which we call paired, right? That was something we needed to change based on which element we were doing, and we found that we actually weren't doing that when we revisited the code for our Slater-type orbitals. We weren't changing this between the paired and unpaired for the density matrix, and we think that may have caused the error. PySCF does do this, so it's much more accurate in terms of the results. So we are reviewing the GitHub repository for our previous code, and we will be returning with hopefully better results and extrapolation of the programs beyond Argon for Slater-type orbitals as well. And I just wanted to conclude by looking at futures with goals 4 and 5. That is, first of all, experimenting with different methods. So we wanted to observe a bit more and experiment a bit more with what PySCF has to offer. The first thing would be looking at the most precise, the most accurate method, which is coupled cluster. That on its own has some variations. The most commonly used is what we call coupled cluster SDT, which stands for single, double, and triple excitations. This is generally considered by quantum chemists and quantum physicists to be the most precise and most accurate post-Hartree-Fock method. And it is included as part of PySCF, but the calculations required are a bit more complex. So we are going to be implementing that over the future. We're also going to be looking at PySCF variants of molar placid and configuration interaction. The other things we're going to be looking at is one thing that Mr. New had recommended to us in our previous colloquium, known as DIIS. This basically enhances the convergence or the value, like the kind of constant value that the self-consistent field method approaches. The last thing we wanted to do is just look at other post-Hartree-Fock methods that are also part of PySCF, as listed on the screen, like quantum configuration, like a quadratic configuration interaction or Kohn-Sham density functional theory, and maybe even other completely different libraries apart from PySCF, like C4's Fortran package, or like the chemistry groups use ORCA, which is density functional theory. So we were thinking of looking at those as well. Our last goal, goal 5, that's more of a long-term goal. The ultimate goal of this program perhaps would be to find, if possible, a model that graphs atomic energy as a function of, mass number or atomic number, or atomic mass or mass number and atomic number, and see if we can actually get a model and then maybe actually graph it or create a polynomial regression. So we've already begun working on that, and as you can see on the right, so this is your restricted Hartree-Fock. This is your data actually for STO3G. And clearly we think there has to be some sort of progression, because it's not like a random result. There is some sort of a progression with these. So we are hoping that to get some sort of a model, maybe by, after we get more data until lanthanum or so, we can focus a bit more on goal 5 as well, and see if we can actually come up with a few, working models perhaps for atomic energy in terms of atomic number. The last thing I would like to do, of course, before I conclude, is our credits. So I would like to thank everyone who made this research project possible. First of all, Dr. McMahon, our advisor, he guided us through the entire process, gave us tips on how to actually go forth and get the data done and how we should get done. And he also kept the team on track and made sure we did our stuff on time as well. So thank you so much for that. We wanted to thank Mr. New. He was the one who gave us the idea to actually pursue correlation energy and these different libraries and see maybe how they turn out. We want to thank ASDRP, who actually provided us the cluster and all the resources and the place to actually carry out such investigation. And most importantly, we would like to thank all of our group members, because without them, we couldn't have done any of this. So thank you so much once more. And that is the end of our presentation. And now we could get started for questions. Thank you so much. I will get started. I've been getting some questions already. So would it be easier to calculate bigger basis sets compared to smaller basis sets? That's a wonderful question. And the thing would be, it really depends. It depends. The thing is, for your smaller atoms, which have lesser electrons, it doesn't make sense having a lot of functions for a lesser number of electrons, because that's just redundant. You take too much time. But for the bigger atoms, which have more electrons, it makes sense calculating bigger basis sets. So in terms of relevance, yes. Would it be easier? I wouldn't say it's easier, because it is quite complex actually calculating the basis sets themselves, but exactly, it makes more sense to calculate bigger basis sets. In terms of like how well the number of basis sets model, the smaller basis sets only have few functions, like I said, for a lot of electrons, which doesn't make sense. It's really hard getting an accurate model. And I think that was the major issue with looking at these. The next question I did get was, apparently I don't have any more questions. Okay, never mind.
Then asked one, do you need bigger basis sets for larger atoms? It is always great to have larger data sets, like it gives more accurate results, but I wouldn't say that it's exactly necessary.
And by the way, for anyone, if you are interested in getting, we'll definitely send the presentation, as well as if you guys were interested on the links we used for our database or our actual data, which is all on one Excel sheet, please feel free to just email us or, send us some sort of a notification on Slack or something. I'd love to send you our data and our presentation as well.
I have a question. This is Mr. Downing. If you believe you're having issues with the server, why am I just hearing it now?
We don't have issues with the server. I think the server is actually working great. We just wanted to get like something which had more. I think our only thing was looking at the runtime. There weren't issues in terms of the actual program itself. It was just loading Jupyter Notebook, which took some time. But I think that's just something that's natural because you're accessing a remote server. So I think we just have to investigate a bit more on getting more efficient runtime analysis, because our previous library was kind of messing up with the runtime. So.
Okay. Then I don't feel quite as bad.
If you wanted to do something to help in that area, you could probably figure out a way to get and report runtimes for various programs that run. If you can do that as a generic job, then we can use it in our stuff, and other people who care about runtimes can do it also.
Okay. You'll have to let me know what server you're using.
The ASDRP server.
That narrows it down to 18 servers.
Put it on all of them.
I think that would be ill-advised.
Perhaps we could dedicate a group for runtime calculations.
Let's have a follow-on conversation.
Sounds good.
I have pairs.
So I did get one question. What are GTO and STO? So I'll just go back to that slide, but those are actually abbreviations for Gaussian-type orbital and Slater-type orbital. And I'm hearing some sort of echo. They're going to mute themselves. I'm so sorry. Thank you so much. So there are two different types of orbitals. Now, the one that you see on the left, that's your Slater-type orbital. And the one that you see in the middle, that's Gaussian-type orbital. And Slater-type is abbreviated as STO, Gaussian-type is GTO. And that's what we were discussing. In our previous semester programs, we use STOs, but PySCF, which is what we're working on now, uses GTOs. And we're trying to compare and contrast them and see, if we can get some data out of it. Any other questions? If not, we can turn it over to the Benson group.
I think we should be ready whenever y'all are done. Ave, how you feeling?
Yeah, I'm good.
Okay,
I think
why don't you bring your presentation down, Vaibhav?
Sure. I did get one last question from Deeptanshu, so I just want to answer that before we just move on.
Go for it.